Hi everyone, in today's video we are going to be talking about the n-queens problem, which is an example of a constraint satisfaction problem. Now, we'll talk about the n-queens problem and what exactly it is here in a second, but it serves as an illustration for how to go about tackling other constraint satisfaction problems. Problems that you've probably seen before, like Sudoku, or even something more general, like what order should I do my assignments in such that I get everything completed before each assignment is due. Now, I'm going to be showing you how to solve problems like that with a technique called constraint propagation and backtracking. Now, that sounds super complicated, but today we're going to be writing a quick Python program that implements that technique and solves the n-queens problem. And hopefully you'll see that it's not as intimidating as it might sound at first glance. So let's get to the n-queens problem. In the show notes, we've included a link to the Wikipedia article that kind of explains the problem, but it should be fairly straightforward enough that you can follow along this video and be fine. What the general gist of it is that we've got a setup. I'm going to call it an n by n chessboard, and we need to place n queens on the chessboard. This is an example of the 5 queens problem, where we have a 5 by 5 chessboard and 5 queens. Now, you can't just place those 5 queens in any which way. You have to place them in such a way that no queen can attack another queen. So our constraint satisfaction problem is assigning locations to the queens, and our predefined constraint is that no queen can attack one another. You can see that this is a solution to the 5 by 5 or to the 5 queens problem, in that no queen can attack another. Just so we're all clear, a queen can attack on the horizontal, vertical, or either of the diagonal axes. So this bottom left queen can attack up and to the right, up, and then to the right. So how would we go about solving this problem if we were just given a blank chessboard? If we were just using our general intuition, and we started with a blank chessboard like this, when we were given no other information, kind of a good first step would be to place a queen on the board at some location. I'm going to choose this bottom left-hand corner right there. So what does placing a queen there mean? It means that we can no longer place a queen along in any of these squares, because if we did, the queens could attack each other and then thus violate the constraint that we were given at the very beginning. So we have to choose some square for the next queen that isn't one of these red spaces. And for example, I'm just going to choose this space right here, and then here are all the new spaces that are attacked by this queen. Now, that in itself is constraint propagation. We've made a decision, added some constraints, right? We can no longer place a queen or in these squares that we used to inform our next decision, being where to place this green queen. And we're just going to continue that cycle. So now that we've propagated the constraints for the green queen, we can choose where to place the blue queen, and then we can choose where to place the orange queen. But we might get to a point like this where we've made all the placements that are possible, right? There's no more open squares on the board. However, we've only placed 4 of the 5 queens. So now is where that second part of the technique comes in, which is backtracking. And that's super simple. We just reverse our latest decisions. So our last decision was the orange queen, so we'll back out of that. Now you'll notice there's no alternative spot for the orange queen, so we'll actually back out of the blue queen as well, and we'll place it somewhere else, like over here. So we'll propagate the blue queen's constraints. You'll notice that it doesn't add any new constraints that we didn't have already. Then we'll try to place the orange queen, and now finally we can place that purple queen up there in the top. Here we go. We've used our intuition not only to solve this particular n-queens problem, but also to model the intuition behind the constraint propagation and backtracking techniques that we can use to solve constraint satisfaction problems in general. So let's recap what we did. We can kind of separate it into 3 distinct stages. Number 1, we modeled the constraint space. Number 2, we added or removed constraints. And number 3, we selected our next assignment, our next placement of the queen. And these sort of 3 steps can be used to solve any sort of constraint satisfaction problem, whether that be Sudoku, whether that be ordering your homework assignments, like we talked about earlier. For the n-queens problem in particular, the constraint space was that chessboard representation. Adding or removing constraints just happened to be marking the chessboard spaces that a queen could attack. And then selecting a next assignment, so our next placement of the queen, was just whatever spaces weren't marked. So now the next step is to take this algorithm, this sequence of stages, and transform that into a Python utility that can solve the n-queens problem automatically and very quickly. And we're going to talk about how to do that next. If you haven't already, now would be a good time to check the show notes and download the files that came along with it. We've given you some starter code, some boilerplate, so that we can dive right in to solving the problem. So I'll give you a second to do that right now. So if you're following along at home, you should now have downloaded both the board.py and the driver.py files. These files contain some boilerplate to get us started. This driver.py file is pretty empty right now. Looks like it's just going to eventually be where we put the constraint propagation logic, but nothing exists right now. The board.py does have some interesting nuggets in it, though. Some interesting and some useful utilities that'll help us get us started a little bit faster. So let's take a look at what's contained in here. So the data that we're storing in this board.py file or class is the n, so what dimension is our board, the number of spaces, so n by n, and then we have these two interesting class variables, constraints and queen spaces. So before we dive into what exactly these represent, let's talk about how we are going to model the problem that we just solved. So let's take a look back at that PowerPoint. I'll pull it up here. So on the PowerPoint, notice that we have this grid, and this was a really useful visualization for solving the problem. How are we going to transform that into a concrete data representation in Python? So what I'm going to propose is that we keep kind of the grid representation, and instead of having blocks that we put on the grid, what we do is we just have a counter for each cell, where the counter represents how many times can this cell be attacked by a queen. Notice that on the empty board, every cell is going to have a counter initialized to 0 because there are going to be no queens anywhere on the board to attack any of the cells. Now, a grid representation is all fine and dandy, but it's going to be difficult to do in Python because you will need to do a two-dimensional array. And you know, not to dive into the internals of Python, but that's not going to be a very efficient solution if we wanted to scale this problem up to larger and larger boards. So what I'm going to propose is that we actually store this two-dimensional grid as a unidimensional array where each grid space gets a unique number. And my numbering convention has just been from left to right, top to bottom, and you can kind of see how these indices propagate across the entire grid. So we'll have a list in Python where index 1 represents this cell, index 17 represents this cell, so on and so forth. And we'll see in a second that we have provided a utility that converts particular rows and columns into these numbers. So you don't have to necessarily worry about that particular logic yourself. I'd also like to add this queens list. And so this will just be a list of the indices up here where we have placed a queen. So over time, we'll fill this up until we hit n queens, in this case 5 queens, meaning that we have completely placed all of our queens on the board. So what will happen when you place a queen? Let's just walk through a quick example. If we were to place a queen at index 0, being this cell right here, what we would do is we would add 1 to every cell where this cell can attack. So that'd be everything down this diagonal, everything to its right, and everything beneath it. And you can see we've incremented the cell counters in this illustration. If we were to add another queen, 11, so that would be right here, we would again increment everything. So in this case, up, down, left, right, and then along both diagonals. You'll notice that some of the counters are now going to be more than one. They're going to be up at 2. And you might be wondering, okay, so if we know that something's blocked, why do we need to count how many? Well, that makes it easy to remove the queens. So for example, let's say that we want to remove queen 0. We don't have to worry about which cell was attacked by which queen. Right now, we can just remove 1 from everywhere that that cell 0 could attack. So that's everything along those original diagonals that we had talked about. And you'll notice that queen 11's attack area is still completely covered. So we didn't really have to worry about which queen was attacking which cells. It just kind of all added together. Another important consideration is what these 0 cells actually represent. And they represent those cells that we can place a queen in safely without another queen attacking them. So the 0 cells are going to be the ones that we try to pick out in the stage 3 of our algorithm, which is selecting the next assignment. And you'll notice that we just covered with that the modeling of the constraint space as the 2 lists, how to add and remove constraints, and how to select the next assignments. And so we've just done that kind of in general here, and let's take a look at how we're going to implement that in our Python program. So if we come over to our Python program, you'll notice that we have that list for the constraints right here. And we have the list for the queen spaces, with the constraint list having all the counters initially set to 0, and we've got 1, 0 for everything in the n by n grid, so that should map nicely. And then we have the queen spaces, which is going to be empty because we have no queens initially. So let's take a look at what stuff we've given you. We've got some move functions, some constraint logic, some utility functions. Within the move functions, we've already given you get possible moves. So we've already defined the logic for how to go over the constraints and return what spaces are safe. Essentially, all this does is picks out what indices contain 0 values. So that should be pretty straightforward. We also have make move and remove move, which adds a queen or subtracts a queen respectively. And then those both trigger the add or remove constraints function, which will add or remove constraints depending on whether it is called from the make move or remove move function. But what we haven't given you is the add or remove constraints logic. We've given you kind of some modularity, saying that you can call this both to add and remove constraints, but we haven't given you how exactly are we going to add 1 across every horizontal, vertical, and both of the diagonal axes. We have given you, though, a function to just add 1, essentially, to a particular move. It's just a nice way of creating some modular code. Nothing too spectacular there. But we do also give you some utility functions that will come in handy. We've got that RC to space function that I mentioned earlier, which will transform a row and a column into its corresponding space. So for example, if we put 0, 0 in here, then we would get 0 back out. If we put 0, 1 in here, we should get 1 back out, so on and so forth. We also have this print utility, which will provide a visual representation of the board. I think I have a little print, so at the final product, when we print out the board, it should look something like this if we were trying to solve an 8x8 board with all of the queens placed in non-conflicting spaces. So let's dive into it. We could start either in the driver or in the board class, but I'm going to start in the board class. I'm going to try to get this constraint logic worked out before we try to think about how to actually solve the problem. So what we know we need to do, if we go back to our PowerPoint real quick, is when we start out with something like this and we add a queen to this space right here, we need to be able to capture the logic of incrementing 1 along each row, vertical, and diagonal. So let's start with the easy stuff. Let's do the row and column. Now, you'll notice, if you think about it, that one way, well, let's go back here, that one way to increment the row and column is to just find out what row and column is a move within, and then just go across the entire row and column adding ones. So for example, if I started here at this space, if this is where I place my queen, I know that my row is 0 and my column is 0, so I should just be able to go over every index in the row and every index in the column and add 1. But the first step is figuring out what row and column are we in, and you'll notice if you think about it that the row can be found pretty easily. We will just take the move, being that number in the this top right hand corner, indicating what cell in the two-dimensional grid. If we take that number and we integer divide it by our n value, right? So this essentially will divide by the n value and then truncate the decimal off. So if we had, like in our example over here, if we are picking 12, for example, we have a 5 by 5 grid, so we do 12 divided by 5. That's going to give us 2.4. When we truncate that, we're going to get 2, and you'll notice that we're in row 2, being 0, 1, 2. So that's the row. Column is going to be something similar. We can just do column is the move, and then we can do modulo, modulo self.n. And that's going to give us our column. So let's take a look over here. So if we had 12 and we did modulo 5, we'll get 2, which is going to be, again, our column here, 0, 1, 2. And so you can try that out for yourself, but that trick does work, and that'll give us our row and our column. So we know that no matter what row and column we pick, we're going to have to add 1 to 5 different indices. So what we can do is we can just have a little loop here. Well, I guess, sorry, let me back up. We need to add 1 to n different indices. So let's make it modular so we can work at any size board. So we're going to say for I in range n, representing this, and we can do them both at once. So this will be, let's see here, we'll tackle the row first, and then we'll do the column next. So if we're going to tackle the row, we can just use our mutation function that we have defined up here. This should be pretty easy to see how those map. And then we're going to use our utility function. Let's see here, rc to space. So if we're going to do the row, we have our row variable. Everything's going to be in the same row, and we can just do I, right? Because we're going to iterate across that row. And we're going to mutate, either add or remove the constraint for every cell in that row. And we do something pretty similar here with the column. We can do self rc to space, except we're going to do I and column. So we're just going to stay in that column, but go through every index in that column and either add or remove the constraint from there. So that's rows and columns, but the tricky part comes in with the diagonals, right? The left and the right diagonals. So I want you guys to think about this for a second before continuing on. I'm going to pause the video real quick, and then we'll go over how to do that here in a second. So if you've thought about this for a little bit, you've probably come to the conclusion that this is actually a pretty simple problem. We just need to figure out where to start, either what row or what column should we start our diagonals in.
I'm going to go about it from the row standpoint. So I'm going to figure out what row should we start I'm going to call it the right diagonal and the left diagonals in. So the right diagonal, let's say start row equals something, and the left diagonal start row equals something. Believe it or not, this is almost as simple as figuring out what row and column you should start in. And in that, it's just row plus column and column, and row minus column. And you can see that that holds true because for every row that you move, you're also going to have to move a column. So our left diagonal is going to start at row plus column, and our right diagonal, our right diagonal is going to start at our row plus column. That's the diagonal that's sloping up and to the right, and our left diagonal, the one that's sloping up and to the left, is going to be row minus column. And then we can just do the same thing that we had done before, except now we're going to be incrementing two things at once, not just I. So we can do mutation fx self.rc to space for the, let's say, right diagonal start row, and then we'll do I there. And then we'll do the mutation fx self.rc to space left diagonal start row I, and then we're going to want to make sure that we increment both of them as well. So rd start row. So this one is going up, so we're going to want to subtract one from the rows. And left diagonal start row plus equals 1, because it's sloping down. If we're talking, as we go across the columns from left to right, the left diagonal is sloping down and the right diagonal is sloping up. Now, for those observant watchers out there, you'll probably notice that this is going to eventually throw an error because our diagonals might be out of bounds of our constraint grid, right? So it's not true that we'll actually have to mutate or add one to every space, or to n spaces in the grid. For example, if our space was up here, yeah, our left diagonal is going to have 5 additions, but our right diagonal is going to have none. So we need some way to handle that logic as well. And what we can really say is actually we can encode that pretty easily. We can just say, if for the right diagonal the start row is greater than -1, then go ahead and do that. Because we're going to be subtracting here, so we want to make sure that it's greater than -1 as we continue to subtract. And this one is going to be less than n, right? We can't be n or equal, otherwise we'll be out of bounds of the grid, because remember, we're indexing by 0. And that should be it. So this is going to be our right diagonal, and this is going to be the left diagonal. But there you go. That's actually all the logic that we needed to add there. That should do the appropriate mutations. So now we can move on to the next component of the project, or I guess of this small demo, which is defining the driver function. So this is actually going to be, believe it or not, even easier than what we just did. It actually has a very nice, elegant feel to it. So let's assume that we've got a board, and we'll call it B. It's going to be an 8x8 board. So for that board B, if we're going to go about placing moves, we're just going to follow kind of the same logic that we did earlier when we were going through the PowerPoint. We're going to say, okay, let's get a move, a valid move. Let's make that move. we'll propagate the constraints. If everything, then we'll try to make another move. If that move works, we'll keep going until we've placed all of the queens. If at any point we run into a configuration that doesn't work, we're gonna backtrack. We're gonna remove the move that we made and try a different move. So in order to try all the possible moves, we've got to have some sort of iteration over the possible moves. So I'm going to say for move in b.get possible moves. So here's where we're going to be trying things. We're going to say, let's say b make move. So this is us not just making the move, but also propagating the constraints. We're then going to say if we're finished, in other words, do the amount of queens equal n. If that's good, we can go ahead and return true, indicating that we've finished our work. If the amount of queens is not n, then we've still got more work to do. So I'm going to say, let's go ahead and place moves again. Now we know place moves is going to return a value, a Boolean value, because we're returning true here. So we're going to have just retval be the capture of that return value. So if retval is true, we want to do something. Otherwise, we want to do something else. Now, if retval is true, that indicates that we've reached the end of our placement. We've found a valid configuration. So in that case, we can just return true here. So if retval is true, we return true. And we bubble that truth all the way back up to the top. Otherwise, we've reached a false. And that means that we need to backtrack. So we can remove the move that we just made. And then our loop is going to come back up and try the next move in possible moves and repeat kind of that cycle. Now, if we get through all of the moves and possible moves and still have not found a valid configuration, we're going to have to return false. We're going to say that some move earlier in this chain, this recursion of placing moves, ended up with an unsolvable configuration, and so there's nothing more that we can do at this point. And that's all there is to it. So I think that if we give this a run, it should print out something that looks like that down there. So let's give this a shot. There we go. We got the exact same thing. So this is a valid configuration of queens. Feel free to double check it. And we implemented it just in a couple lines of code. Now, you can take this sort of constraint propagation logic and reuse it in any sort of constraint satisfaction problem. In fact, this is all you really need to have. Now, every different situation is going to have a different way to propagate constraints. For example, the way we propagate constraints in the n queens problem is going to be very different from how you propagate constraints in, for example, a Sudoku board, or for that running example of how do you order your homework assignments. However, everything's going to come back to that three-step algorithm that we talked about earlier, which is figuring out a way to model the constraint space, add and remove constraints, and then select the next assignment. If you can do that, which looks like this in Python code, you can solve any constraint satisfaction problem. That being said, some might take longer than others, depending on how efficient your solution is or how complicated the problem is. But there's nothing really more complicated than that, at least for a very general, high-level solution. And I'll leave you guys with that. Look for my next video coming out in a week or so.